We have 2 students only so far. Okay. So we are here on Wednesday. I'm gonna bold face this thing here. And resistance measurement. Yeah, that's the lab resisted B fields. Let's see, I'm gonna put B forces. Okay, B is means magnetic. That's the representation for the magnetic field. Let's see, more students, Sky is coming. Huh. Strange. Okay. That's why we are right now. Okay, lab 3 is going to be chapter 20, material related to chapter 20. But I want to start chapter 21. In this first hour, we start chapter 21, and then we do chapter 20. And then we do lab 3, which is material for chapter 20. Okay, so that's the situation. Let's get the notes. I do not know if you notice it, but I cut down. I don't have the notes for chapter for the year 2023 in this version here, right? In this version, I'm not mixing up in this new version of this course. I'm no longer mixing up the material that I taught in 2023. So just to let you know. And okay, right here. Okay, this one is going to come later on, not yet. Okay, it's going to come later on after, you know, we cover it. Here you go. We will cover it after chapter 21. The chapter 21. That's where alternating circuits come along. We have to cover the concept of magnetic field before we cover alternating circuits. The book didn't do it this way, unfortunately. But these are all the material that you have to worry with, the section of this one, right? This is the material that you have to worry about chapter 20. You don't have to worry about this one. Okay. But it's still lots of information, especially if you're seeing it for the first time. Let's insert our page break here, and we start March 13, 24. That's Wednesday. And we start magnetic field. Magnetic field is abbreviated by the letter B, B field. Magnetic field and magnetic force, B field. Let's put plural fields, right? And magnetic force, B fields and B force. B is the abbreviation for magnetic. And let's take a look at the book first. Here you go. Magnetic fields are known for a long time, okay? Magnetic force and magnetic field are known at least since antiquity. At least since antiquity. And if you watch that TV series about Marco Polo in Netflix, yeah, in Netflix, it's a very good TV series. I like it. I watch it completely. You know, Marco Polo, when he was going to the East, right? I grew up thinking that Marco Polo had visited China. That's what I grew up thinking, okay? But then I learned that was not true. Actually, Marco Polo went to Asia and he stayed in the court of Kublai Khan, who was a Mongolian leader, right? Who was the Mongolian king. I didn't know that, you know, until recently I thought that Marco Polo was visiting the Chinese, was staying in the court of the Chinese, but in reality, he was staying in the court of Kublai Khan, the grandson of Genghis Khan. It's amazing what we think when we are younger, right? And later on you discover to be slightly different. And so if you watch that TV series, you're going to see that the Mongolians already knew about the compass, and they dramatized that in the TV series. They use the compass to navigate in that vast desert, in the vast steppes of the Asia, Central Asia. It was very difficult to navigate there, especially because, and also at that time we also had the Silk Road, the Silk Route, right? And now the Chinese are trying to resuscitate this Silk Route with another name. Okay, the Silk Route that would expand the whole globe. That's what the Chinese are trying to do now. But that's an interesting piece of information, right? Marco Polo stayed in the court of Kublai Khan, the Mongolian king, grandson of Genghis Khan, right? And he witnessed the fact that the Mongolians already used the magnetic field to orient themselves. They even used the compass, which was a Chinese invention, by the way. The compass was a Chinese invention. And it's a fascinating story. Okay, so that back then, in the 1200, they already used the compass for navigation purpose, but not in the sea. They would use the compass for navigation purpose inland. Okay, it was the Portuguese and the first civilization, the first society to start using the compass for navigation in the high seas. Okay, which, like I said, the compass was a Chinese invention, and that was adopted by the Mongolians. After the fall of the Roman Empire, the Arabs also start to work with the compass. Some books say that the compass was an invention of the Arabs. No, it was not an invention of the Arabs. Okay, and then finally, it took the Europeans to put the compass to real practical use in the high seas, and that started with the Portuguese. They start navigating, trying to find a passage to India, right, during the age of discovery. And the magnetic field is central to all these developments in society. If it weren't for the existence and our knowledge of the magnetic field, we wouldn't be able to navigate on the surface of the Earth. Okay? If you want to take a quick look here, a magnetic field, the history of magnetic field, right? Go to Wikipedia. They have a nice article in there. I'm quite sure there are other references as well. I am mostly interested in the history, okay? The history of magnetic field. While magnets and some properties of magnets were known to ancient societies, the research of magnetic field began in 1269 when French scholar Petrus Peregrino de Maricourt mapped out the magnetic field on the surface of a spherical magnet using iron needles. You know, unfortunately, they don't say anything about the, okay, you have to go to the compass. Okay, you have to go to the compass. That's the wrong, that's not the correct one. Okay, so let's go to compass. Compass here in there. So real scientific research started in the 1200 by the French, right, of the magnetic field. But what about the compass? Let's take a look here at the history of the compass. The first compasses in ancient Han Dynasty, China, were made of lodestone. Okay, is a natural mineral that is magnetized. That lodestone is. But the Greeks also knew about this lodestone. It's not just the Chinese. There you go. But what was the difference between the Chinese and the ancient Greeks, right? The difference is that the Chinese were able to create a compass. Okay, were made of, and those compass were made of lodestone. Lodestone was already known by the ancient Greeks, a naturally magnetized ore of iron. Later compasses were made of iron needles. Okay, first lodestone, pieces of lodestone, and then pieces of iron needles, magnetized by striking them with a lodestone. That appeared in China in 1088. They say Han, let's see, Ancient Han Dynasty. Let's see when was the Han Dynasty is. Okay, it was in BC. Okay, BC. Imperial dynasty that ran from 202 BC to 9 AD and 25 AD to 220 AD. So has been, the first compasses, okay? Do the Song dynasty. Dry compasses began to appear around 1300 medieval Europe, in medieval Europe. Most likely it was Marco Polo who took it who introduced that in Europe and the Islamic world. Okay? This was supplanted in the 20th century by liquid field magnetic compass. Here you go, here's the liquid field magnetic compass. Model of a lodestone compass from the Han Dynasty. Okay, here you go, the shape of a little spoon, right? So, okay, and so that part of the history of magnetic fields. Magnetic forces were known by the ancient Greeks. Ancient Greeks who observed that naturally magnetized minerals observed that a naturally magnetized mineral, lodestone, exerted a force in iron filings, just like you saw in that picture of Wikipedia. Okay, let's see if I have it here. Magnetic field. Going back there to magnetic field, right? Let's see. Its own history. Where is that? No, it's not here. More students coming in. History must be here. No, it's not here. Magnetic field should be compass. See, and then we have history here. Where's my lodestone? Oh man, do you remember where was that picture of the lodestone? I really thought it was cool. Magnetic field. That's the. Let's see. Well, if I struggle to find it, I'm just gonna move forward. And let's see, lodestone. Let's see, lodestone. Naturally magnetized. Here you go. Okay, it was this topic here, lodestone. That's where the picture was. And here you go. It's just like our magnetic filings, right? Or in this case, would be iron nails attracted to the lodestone. And naturally magnetized piece of mineral of the mineral magnetite. They are naturally occurring magnets which can attract iron. The property of magnetism was first discovered in antiquity through lodestones. And then we have a reference here. Okay, pieces of lodestone suspended so they could turn were the first magnetic compass. Think about that, right? You suspend a piece of lodestone with a string, right? And if the lodestone were light enough, they would align with the Earth's magnetic fields. And their importance to early navigation is indicated by the name lodestone, which in Middle English means coarse stone. Okay, that's what lodestone means. Course stone, the stone that plots the course for navigation purposes. Importance to early navigation. Navigation here doesn't have to be in the seas, in the water. It can be navigation in the land as well. Okay. Or leading stone, from now obsolete meaning of load as journey, way. Lodestone is one of only a few very minerals that's found naturally magnetized. Magnetite is black or brownish black with a metallic luster. A moss hardness of 5.5 to 6.5 and a black streak. Okay. Then they say how lodestones are formed. One of the here you go, history. One of the earliest known reference to lodestone magnetic properties was made by the 6th century BC Greek philosopher Thales of Miletus. Okay, ancient Greece. So that's how far we know, how far in time we know about the magnetic properties of lodestone, whom the ancient Greeks credit with discovering lodestone's attraction to iron and other lodestones. The name magnet may come from the lodestones found in Magnesia, Anatolia. Okay, city of Anatolia, where we have those weird formations in Turkey. I don't know if you have seen that. The region of Anatolia in Turkey. Anatolia, there you go. It's known as Asia Minor. It's a large peninsula. No, we're not going to get into that, right? The earliest Chinese literary reference to magnetism occurred in the 4th century. Book of the Devil, Valley Master. In this chronicle here from the 2nd century, explicitly stated that the lodestone make iron come or it attracts it. The earliest mention of a needle's attraction appeared in a work composed between 20 and 100 AD. A lodestone attracts a needle. In the 2nd century BC, Chinese geomancers were experimenting with the magnetic property of lodestone to make a south-pointing spoon. Did you see that spoon there? The picture of the spoon in the previous article, right? Let's see if we have it here. Here you go. That's the little spoon here that they're referring to from the Han Dynasty. Okay. Here you go. South pointing spoon for divination purpose, not for navigation purposes. Very important. Compasses started as a device that were used not for practical navigation applications, but just for divination. They want to orient properly the furniture in their houses, right? And so they would use those properties of the lodestone to find out what would be the proper orientation of the furniture in the house. That's what they call divination. When it's there's a name for this type of divination. I believe it's someone there must know, right? I don't remember it right now. The name, Feng Shui, I guess. Maybe it's Feng Shui. Feng Shui. Let's see, Feng Shui. The books that we have in literature, yeah, maybe it's not Feng Shui. Sometimes the Chinese geomancy, yeah, geomancy, okay. And they also said geomancy here. History. Not this one here, okay. Chinese geomancers, okay. Yeah, it's Feng Shui, definitely. When it's placed on a smooth bronze plate, they put on a bronze plate. Isn't that nice? That's because there was very little friction between the spoon and the bronze plate. Okay, later on they start to put very light, pieces in water, and due to the surface tension, the piece of lodestone would not sink due to surface tension. Okay, the spoon would invariably rotate to a north-south direction. While this has been shown to work, archaeologists have yet to discover an actual spoon made of magnetite in a hand tomb. Okay, based on the discovery, Olmec artifact, even here in the Americas. Okay, the pre-Columbian civilizations. Based on his discovery of Olmec artifact, a shaped and grooved magnetic bar in North America, astronomer John Carlson suggests that lodestone may have been used by the Olmec before the Mayas, right? Before the Aztecs, more than 1,000 years prior to the Chinese discovery. Oh, so the Americans were ahead of the Chinese in terms of magnetic field, right? In terms of compass. Carlson speculated the Olmecs for astrological or geomantic purpose used similar artifacts as a directional device or to orient their temples. See that? Just like the Feng Shui, right? The dwellings of the living or the interments of the dead. Detailed analysis of the Olmec artifact revealed that the bar was composed of hematite with titanium lamellae that accounted for the anomalous remnant magnetism of the artifact. Okay, that's an interesting piece of information, right? So let's go back here. What really matters, right? Magnetic forces were known by the ancient Greeks who observed that the naturally magnetized mineral lodestone exerted a force in iron filings. Other civilizations followed. Civilization followed until it was discovered. Other civilizations followed. When it was discovered, that pieces of lodestone would point in the north south direction. Okay. This device started to be used as a rudimentary compass. That was initially used for divination purpose, and later on for navigation purpose. Remember, wasn't for the compass, the Portuguese wouldn't be able to venture out in the high seas. Weren't for the compass, we wouldn't be around. Okay, weren't for the compass, the Europeans wouldn't have discovered the Americas. Navigation compass purpose. So, what you have to know about? Here you go. We spent already almost half an hour talking about that, right? So let's move on. Here you go. You might want, here you go, magnetic fields. Okay, here you go. Here's an illustration of a compass. Remember, you can also suspend this needle from a thread, right? If you suspend this needle from a thread, it will also orient in the north-south direction. So what do you know? What do we need to know about the magnetic field? What do you need to know about the magnetic field? Okay. Okay. Unlike the electric field, which is generated by positive and negative charges, okay? There is no such a thing, and I'm even going to emphasize positive and negative generated by isolated, okay? Positive and negative charges. I want to emphasize that here. There's no such a thing as a positive and negative. There's no such a thing as an isolated positive and negative magnetic, not magnetic charge, but we use the word pole. But let's put a charge as well, slash charge. Okay, that's the first law. That one of the laws, that is one of the laws of electricity and magnetism. Okay. So far we have been talking about only two laws of electricity of magnetism. One, laws of electricity and magnetism. Okay, one, Coulomb's law. Coulomb's law or Gauss's law. They're the same law. It's just they're formulated in a different mathematical fashion, okay? Coulomb's law or Gauss's law. Okay, remember Gauss's law, how is it spelled out, Gauss's law? The format, the mathematical format. Remember, the mathematical format of these two laws are different, but they are the same law, okay? Although the mathematical format of these laws are different, they express exactly the same thing. Although the mathematical format of these two laws are different, they are exactly the same law. They are exactly the same law. And now we have this other law of electricity and magnetism that states that there is no isolated magnetic pole. Okay. So by the same token that we define an electric charge, right? We also define a magnetic pole, positive or north, and negative or south. Okay? But very important, the north and south pole, they do not, according to this law, according to this new law, the north and south pole do not occur in isolation in nature. We never observe that. In other words, we never observed that. It was never observed in nature. There are scientists there are scientists that want to prove the existence of magnetic monopoles, but they have yet to provide some serious evidence that is recognized by the scientific community at large. Okay. And also, that's the first thing that you gotta take home. No north, and I'm going to illustrate that in this way. Here you go. There is even going to put it in a different way here. Here you go. We can put this way. Magnetic dipole, two poles. That's what we observe in nature. But if we are going to break down, to cut this magnetic dipole, that's why it's called dipole, because it has a positive and a negative polarity, or a north and south polarity. If we break it down in half, you'll never be able to isolate the north from the south. Every time that you break it, the south forms naturally, and the north also formed in the lower part of this magnet. And if you keep on breaking, it's still gonna form north and south polarity. This is like I said, this is a law of nature. Okay, and what else can we say about? Okay, those magnetic poles, they do generate a magnetic, not just a magnetic force, but also what we call a magnetic field, right? And that's how we illustrate the magnetic field of a magnetic bar, of a dipole magnetic bar. That's how, those are the lines of magnetic fields, which is rather similar to the lines of an electric dipole. The shape is relatively the same. Okay. Center it. Okay, so the magnetic field lines come out from the North Pole and converge towards the South Pole. If you get a magnetized needle next to a magnetic dipole, it is going to orient tangent to the magnetic field lines. So that's how we map the magnetic field lines with those magnetized needles. And here you go. Here's representation of the magnetic needle. And here's the vectorial representation of the magnetic field, tangent to the magnetic field lines. One magnetic field here, another magnetic field here, another magnetic field here. Okay. So magnetic fields start at the north or positive pole of a magnet and converges towards the south or negative pole. Okay. Although the behavior is similar to the electric field of an electric dipole, these two fields arises in different ways, in two different ways. What I mean, two different ways, two different sources. Okay, we say that. Okay, we say the following, right? And already discussed that, right? The source of an electric field is a positive charge. We say that the sink of an electric field is a negative charge. We say that the source of a magnetic field is the north pole of a magnet. And the sink, right? The sink of a magnetic field is the south pole of a magnet, but we can elaborate that even more. You know, I'm going to write that down here. Okay, items 3 and 4 is not the whole story. It's not the whole story. And we are going to elaborate on that. So, and we are going to elaborate on that very soon. We're going to elaborate on that very soon. In reality, you know, there is a lot. In reality, there is another law of physics that elaborates on the source of the magnetic field. Okay, there's another law of physics which we're going to see very soon. 927. So that's the ideas, the basic ideas of a magnetic field that you have to understand, that you have to memorize for now to progress in your studies, okay? I'm getting here today is the okay, so one more. magnetic field and force. I'm going to elaborate a little bit more on this Coulomb's law, Coulomb's or Gauss's law, right? Coulomb's or Gauss's law is something like that. The electric flux is equal to that, right? That's the mathematical expression of the Coulomb's and Gauss's law. That's the mathematical expression of Gauss's law, right? Coulomb's law is simpler than that, but Gauss's law is broader. It's broader than Coulomb's law. And because there is no isolated magnetic monopole, okay, the magnetic flux is expressed in this following way. Does it make sense? We have a zero here on the right side. The zero states that there is no magnetic monopole in isolation, but only magnetic dipoles. Okay. In the case of an electric dipole, if the electric flux is going to be zero, if we put a surface encompassing the two charges, positive and negative, okay? Okay, just like then, that's the differences between electric field and magnetic field, right? Differences, right? Differences between electric field and B field, magnetic field, right? One, no isolated magnetic, isolated electric charges versus isolated electric charges exist, okay, versus isolated magnetic charges do not exist. Okay, that's a difference. Similarities between electric and B fields. And B field. Put this way here. Two electric charges and two magnetic charges. There's a similarity, right? Positive electric charge and positive magnetic charge. Positive or north, right? Or north magnetic charge. You want to put between quotes. Another one. Negative electric charge and negative or south magnetic charge. Positive electric charge attracts a negative electric charge, right? And right? And positive, similarly, positive magnetic a positive, let's put it this way, a positive electric charge, negative electric charge. Similarly, a positive magnetic charge attracts a negative magnetic charge. Okay? And vice versa, right? And vice versa. Vice versa. So similarities and differences. Let's see. Now, some time ago, the Chinese and the Mongolians, whenever they observed that a lodestone would orient in the north-south direction, they came up with this crazy theory that is accepted today, okay? That the Earth behaved just like a giant magnet. Okay, it's not just the Earth, by the way; it's the other planets as well, and the Sun itself too behaves as a giant magnet dipole. So here you go. Here we have the Earth, and here we have the axis of rotation of the Earth. Okay. At the point where the axis of rotation intersects the surface of the Earth, we have what we call the poles of the Earth, the geographical pole. We call it the geographical pole of the Earth, the north geographical pole and the south geographical pole. Okay. But then there's something else. Here we are talking about the geographical pole. But like I said, the Mongols and the Chinese, when they observed that a magnetized needle would point towards a given direction, they came up with this crazy hypothesis that the Earth behaved like a huge magnet. Let's see if I can do that. Okay, let's see if I have it. So now I'm gonna put it here. Oh, not what I want. Oh, okay, now I need the magnet bar. Okay, I got it. Here you go. Here's the magnet bar. Just like that. The only difference is that what we call the north pole of our magnetic bar, it's inverted with respect to the geographical north and south pole. Okay, that's the only difference. So your magnetized needle, it doesn't point towards the north, it actually points toward the south magnetic pole. It points to a region that's close to the north geographic pole. And this region is called, this point in space is called the south magnetic pole. Okay? And that's something that, here you go, positive and negative. See that? The positive pole, the north pole, is nearby the south geographic pole. The north magnetic pole is nearby the south geographic pole. We also have here that the north geographic pole is nearby the south magnetic pole. I'll put the north geographical pole here, so it looks better now. Okay, I put this different. And by the way, this polarity, this magnetic polarity changes with time. Every now and then the Earth swap its north and south pole. It takes something like 100 million years, something like that. But it does happen. We do have evidence, geological evidence that something like that happens. No field, no field. Okay, yeah. Some time ago, yeah, the Chinese and the Mongols, hypothesized that there is a huge magnet that has its magnetic with a magnet pole, with a huge magnet with its magnetic pole nearby the geographic pole. Okay. This they discovered by observing the magnetized needle of a compass. This is discovered by this they did that, deduced it, right? By observing the magnetized needle of a compass pointed to a direction very close to the true north. Okay, the true north is determined by the polar star, right? True north, the true or geographic, let's put here, or geographic north. Recall from your astronomy classes, right? That the geographic north is determined by the position of the polar star. In this case, what's the name of the polar star? Oh gosh, I forgot the name. Polaris. In the northern hemisphere. Okay. So there is small difference between the geographic north and a small angular difference. In other words, there is a small angular difference between the direction of the geographic north and the magnetic south. Small, okay? And because we have this small difference, we can use a compass to navigate at places that are very far away from the poles. Okay? It was at this moment that people realized that a magnetized needle could be used as a navigation tool. Before then, we used only the stars. Okay. So whatever I mentioned, I'm gonna type it here as well. Okay, a little bit of history here. During the Middle Ages, the Arabs took over the world, right? The Europeans were no longer the masters of the world. With the dissolution of the Roman Empire, the Arabs took over and they started to get in touch with the Chinese and the Mongols. In that TV series, Kublai Khan even mentioned that he couldn't understand why the Europeans and the Arabs are fighting each other because of religion, you know. It was really nice. Kublai Khan mentioned that in the TV series. I do not know if it's a historical record or if they just put something like that to dramatize. And Kublai Khan himself, apparently, he was a very tolerant towards religions. Okay, it's a huge empire. The Mongol had the largest empire on the history of the earth. We don't say much that, but the Mongols had the largest empire in area-wise, right? And Kublai Khan in that TV series, he was looking for, you know, he has all sorts of priests in his court. He had a Buddhist priest, he had a Muslim priest, and he still couldn't get his Catholic priest in his court. He wanted that. That's how tolerant he was towards religions, right? At least in the TV series. So during the Arabic hegemony, the civilization came in contact. The Arabs came in contact, right? They came in contact with the Chinese and the Mongols and the Indians as well, right? The Indians as well. The Arabs had commercial posts there in India and other places, and they learned about the magnetic compass, and they started using it. And then when the Europeans rose to power, when the Europeans came in contact with the Arabs, they are also exposed to the magnetic compass through the Arabs. It was not just Marco Polo going to Kublai Khan, going to Mongol and becoming exposed to the magnetic compass, but the Europeans also became exposed to magnetic compass through the Arabs. And it was that the Portuguese that started using this invention to navigate the Atlantic Ocean. They would call at that time the Atlantic Ocean, they would call it the Ocean Sea. That's how Columbus would call the Atlantic Ocean, the Ocean Sea, the so-called, then called settling colonies in Africa and Asia. Okay. What else you have to know, right? Here we go. In the case of the Earth's magnetic field, the north polarity of Earth is nearby the south geographic pole, and vice versa. We also know that this magnetic polarity has changed several times during the Earth's geological history. Okay, 9:45. So you know now that there are lines, and that let's go here to the book, right? Here you go. That's what those few chapters mention. Okay, here you go. The lines of magnetic poles, magnetic fields. That's one type of magnetic bar. This is another type of magnetic bar. Note, see, this one is called a dipole, magnetic dipole. It's called a magnetic dipole because the field distribution, the magnetic field distribution is very similar to the electric field distribution of an electric dipole. And now we have this other type of configuration that produces a uniform magnetic field between those poles. See that? Okay? Whenever the poles are very close by each other, it produces a uniform magnetic pole, and it behaves just like your capacitor. Here's the filings, iron filings around the magnetic bar. They trace the lines of magnetic field. Okay, so, and that, here you go, the Earth's magnetic field. See the polarity here inverted, north and south, right? If we are somewhere around here, let's say here in California, right? This angle here is the deviation of your magnetic north toward the true north. This deviation in California is something around 10 degrees only. Okay, but if you are exactly here at this position here, right, anywhere along this line here, the south magnetic pole is just in front of the north geographic pole. So your magnetic compass will point exactly towards the geographic north and south, okay? That's because the pole, magnetic pole, is going to be in front of the geographic pole. So if you are navigating, right, either a ship or an airplane, you have to know that stuff. And we do have animals that they do use the magnetic field of the Earth to navigate throughout the Earth, okay? Like the lobsters. Lobsters use Earth's magnetic field to navigate and determine their geographic position. It's not just the lobsters, but also there are some bacteria called magnetostatic bacteria that they orient themselves according to the magnetic field. Okay, So the way that that's just the introduction of magnetic fields. And now we're going to get into what really matters at the, mathematically speaking, right? Here you go. So here's this chapter 21, right? There is a magnetic field and there is also magnetic force among magnetic bars. Oh, and there is one more. Oh, and I forgot to put one more thing here. Attract a positive electric charge attracts a negative electric charge. Like electric charge repel each other, right? Similarly, like magnetic charges repel each other as well. So there are lots of similarities between the magnetic and the electric force. Charges repel each other. Repel, not each other, but repel one another, right? One another. It would be better. Repel one another as well. That's another similarity. And now we're going to get into the real mass of the chapter. Okay, and that's when we start talking about the magnetic force. There is a magnetic force, and not only a magnet attract or repel another magnet, but a magnet can also apply a force to a moving electric charge, okay? Let's put it this way. Not only a magnet may attract or repel another magnet, comma, it may also exert a force in a, but don't forget, moving charge, a moving electric charge. The charge must be moving to feel a force due to the magnetic field, okay? And that's another law of physics as well. And this is another physics as well. This is another law of physics as well. This is another law of physics as well. But how does this force behave? I'm going to show here go lines of magnetic field of the Earth. Right here you go, negative bars. We mentioned about that, right? Negative poles repel each other, positive poles repel each other, positive poles attract a negative pole. And now let's talk about the charge. Suppose that we somehow can create a magnetic field in space. Okay, if a charge is at rest, it doesn't matter if it's positive or negative, the charge is not going to feel any force whatsoever. Simple enough? Okay. Now, suppose that this charge now is moving along the fields of the magnetic field lines, parallel. It still doesn't feel any force whatsoever. That's what we observe in practice. Okay. But if the charge is moving perpendicular, the vector velocity is perpendicular to the magnetic field lines, now this force is going to be maximum. It's going to be given by the charge value, the velocity, and the magnetic field. Okay, that's the velocity vector. And let's see. And the direction of the force is going to be given by, let's see here. I have the wrong direction. I have the wrong direction here. It's given by the, oh no, I have the right direction. It's given by the right-hand rule. Okay? You lay down the palm along the velocity vector, crosses your palm towards the magnetic field line, and the direction of your thumb points in the direction of the force, of the magnetic force. That's how we express it in mathematical terms, V cross B, okay? And we can go back here. If the force, let's see, if the charge is moving, it's all documented here, what I showed to you there. If the charge is at rest, there is no magnetic force. If the charge is moving parallel to magnetic field lines, there's no magnetic force either. However, if the charge has a velocity vector component that's perpendicular to the magnetic field lines, there will be a magnetic force. The force will be maximum whenever the velocity vector is perpendicular to the magnetic field lines, and it will be given by that. Okay. The generic expression is this one right in here. QVB times sine of theta. When theta is equal to 0, the force is equal to 0. When theta is equal to 90 degrees, the force is maximum, QVB. Okay? And the direction of the force is given by the right-hand rule, obtained by the following procedure, Point the palm of your right hand. Okay, point the palm of your right hand along the direction of the velocity vector. Move the palm of your right hand towards the magnetic field vector. The direction of your right thumb will point in the direction of magnetic force. The book uses a slightly different procedure of the right-hand rule. Okay, so let's see how it does. But the result is going to be the same. Okay, let's take a look here. Here we go. Okay, same thing that I mentioned, right? See that? The force, zero force, because the velocity vector is parallel to the magnetic field vector. Velocity perpendicular, the force is maximum. Even if the velocity makes an angle with the magnetic field, okay, like here, here's the velocity vector right in here. You still have a magnetic force, but it's gonna be weaker than this one here, okay? And let's see, let's take a look at the right-hand rule. Here you go. He displayed the right-hand rule in a slightly different way. V first, B next. Okay? The result is going to be exactly the same. Okay? Lay the thumb along the velocity vector line, the velocity vector. Lay the rest of the palm along the B field. And the magnetic force is going to be away from the palm of the hand. That's another way of using the right-hand rule, okay? So I think we came to a point where we can take a break. This is, let's see. Let's break it down into lecture, right? And let's see. Today is the 13th. Any questions before we proceed? Let's see, we have 8 students today. I'll take attendance again when we return for the lab. Jacqueline, are you there? Hello, Jacqueline. Just say you're there, or type it there in the chat window, right? You want to put a star here in your name. Let's go for Sky.
Here.
Thank you, Sky. Next is Vanessa Escalera. Now it looks like Vanessa stopped coming, right? Ashley is here, right? Ashley, just say hello. You're there. Hello, Ashley. Okay, let's start here. Your name, Ashley. Corina, are you there? I can't hear you, Corina, if you're talking. Oh, here you go. You type it here. Let's see. Good. Thank you, Corina. Norberto Lopez.
Yeah, I'm here.
Thank you, Norberto. Vanessa Mena. Hello, Vanessa. I'm gonna put a star here, Vanessa. Name Yorgo. Are you there? Looks like Yorgo is not here today, right? Licel. Thank you, Licel. And Paul Zapata. Thank you. So let's see. 3 students didn't answer. Okay, so let's go for our break. 9:59 and break. Let's put 10 o'clock, 10 a.m. to 10:15 a.m. And I see you in 15 minutes for the lab. See you shortly. Oh, interesting. Oh, that's why. Okay, now we can pause. I am back here. 8 students. Okay, Yorgo is not here. Vanessa is not here. Good. So what I'm going to do now, lab 3, right? Lab 3. Let's take a look at the lab resistance measurements. That's the lab that we're going to do. Lab 3 resistance measurements. Okay. So you already know, the digital multimeter that I introduced to you, digital multimeter, you already know, right? You already know that the digital multimeter, DMM, that I introduced to you can make measurements of voltage. Okay, in this, when you make a measurement of voltage, we call it the digital multimeter behave like a voltmeter. Okay, but it can make other measurements as well. Okay, depending on the device that you have, on the DMM, right? On the DMM that you have, it will be able to measure the following quantities. 1, voltage, resistance. It will also be able to measure current. Okay, here When we measure a voltage, we call it as a voltmeter, right? When we're measuring the current, we call it a ammeter. There's no special name for the device when we use it to measure resistance. But there are a few other that you also can measure capacitance. I have seen voltmeters that can measure capacitance. We don't have a lot of those out there, but they exist, okay? But definitely those three, digital multimeters, DMM, will definitely measure those three: voltage, resistance, and current. And capacitance, what else can you measure that? You can measure frequency of a circuit. Frequency of a circuit. That's displayed in hertz. I usually use that feature to measure the intensity of my light sources. Okay. And what we're going to look at today is measurement of resistance. I'm going to put the current as the second one because I measured that before the resistance, right?
Professor, can you share your screen, please?
Oh, okay. Thank you.
Yeah.
Thank you. Let's see. I thought I had. Okay. What about now? I forgot to click it. I had it ready to share with you, but forgot to click it. Now you can see, right? So let's okay, so lab 3, resistance measurements, right? You already know that the digital multimeter that I introduced to you can make measurement of voltage, but it can make other measurements as well. Depending on the DMM that you have, the DMM will be able to measure the following quantities: voltage, current, and resistance, capacitance, and frequency of a circuit as well. And some fancy multimeter that costs like $3,000, it will also be able to measure the electric field, okay? But it would be a very expensive device. I have seen that. There are fries. I didn't buy it. I have another one. It's not I have a device here. I have a different device that measures the electric field here at home that I bought as a project. But it's not, a handheld multimeter like this one. It's something bigger. Okay, and we have a device that measures electric field there at the college as well, in the physics department. And so we'll concentrate here on the resistance. Let me show you. I'm going to switch back to my. I'm going to stop sharing so you can see back. Here you go. Here's my multimeter, right? See here. I'm not pin. Okay. I'm gonna stop blurring my skin. Okay, screen. Okay, here's my multimeter. You can see that here you have measurements of voltage, the letter V. Okay, the letter V. This one here, there's a little twig in there, like a tube, right? That's for AC current. And this one here is for DC current. Okay. Voltage. This omega here is for measurement of resistance. And then we must have another one for current as well. Let's see. Oh, it's strange. This one doesn't have. Oh, yeah. Oh, interesting what they did here. See, this one here is for amps, DC. Amps, voltage, and we call it ohmmeter. Ohmmeter. Okay, what else do we have here? We have frequency here. This one does not have frequency, unfortunately. Must be another one that I have for frequency. I need to measure frequency all the time with my experiments. But this one doesn't measure frequency, unfortunately. It doesn't have capacitance, doesn't measure capacitance either, okay? But measure those three basic ones. So all you have to do is to point this guy here to measure current, right? To measure voltage. We're just talking about DC current, DC voltage, and resistance. Resistance, we call it an ohmmeter. Let's write it down here. Ohmmeter. And I have to share the screen. Let's blur my background. And I'm gonna upload. And how are you going to do? How are we going to do that? Right? In an actual experiment. In the classroom, I provide my students with 6 different resistors. And they use the DMM to measure their resistance, their individual resistance. And the resistance whenever they are connected in series and parallel, okay? That's how I do it in my actual experiment. I do the following. One, provide my student with 6 different resistors. They use the DMM to measure the individual resistance of each resistor. They use the DMM two. I'm gonna put like that. 2, 1. Measure the individual resistance of each resistor. B, measure the resistance. Of 2 resistances connected in series. And 3, measure of 2 resistors connected in parallel. So that's what we are going to do. Oh, there is one more step too, and there is one more step before provide the student with 6 different resistors. Each resistor has its own color code that codify the manufacturer resistance of the device. Right? And the students use this color code to determine the resistor's resistance. Okay? So 2 different ways of finding out the resistance of a resistor. Either with the color code or using the DMM. It's far more practical and quicker to determine the resistance of the resistor using a DMM, okay? I'm going to write that down here. It is far more practical and quicker to determine the resistance of the resistance using the DMM. And let's see. The students here, I'm elaborating here, right? Use 2 different methods to determine the resistance of the resistors. the resistance of each individual resistor, right? Using its color code, using its own color code, and using the DMM. Okay, so using the DMM, they measure the individual resistance of each resistor. They measure the resistance of two resistors connected in series and measure the resistance of two resistances connected in parallel. It's far more practical and quicker to determine the resistance of the resistance of the resistors, right? Using the DMM. And that's what we're going to do today. Let me get all that spreadsheets that you're going to need. Lab reports, raw data. Let's make sure everything is in good shape here. Let's see, one. Here, go, right here, one. Yeah, nothing bad here. That's how the spreadsheets look like, okay? I'm gonna brief you on the color code of the resistors and what it means, how they display it there. Here you go, group number 2. No. Group number 3. Here you go. We have only 3 groups. Yeah, everything is fine. Let's take a look here at this attendance sheet. Of attendance. Data sort, column B, name, group number. Here you go. Yeah, we have only 3 groups here. Let me take attendance again. Today is 13th. Jacqueline, are you there? I can see Jacqueline here. Hi, Jacqueline, say you're there. I'm gonna put a star here in your name for now. Yorgo is not here, right? Lizelle? Yeah, Lizelle answered, right? Oh, Jacqueline answered. Okay, what about Lizelle? Okay, let me put a star in Lizelle's name for now. Paul Zapata? Okay, next, Vanessa Escalera. Vanessa Escalera, no longer around. Norberto Lopez. Hello, Norberto.
Yeah, I'm here.
Okay, thank you. Vanessa Mena.
Here.
Thank you. Sky.
Here.
Thank you. Ashley. Thank you, Ashley and Corina. Okay, so 8-7 on. Okay, that's because one of them didn't answer. Okay, let me see. Group number 1 has 4 students. Maybe let's see, Lizelle. Okay, thank you, Lizelle. Okay, group number 2, we have 2 students, and group number 3 have 3 students. Okay, I will upload your spreadsheets right now. Drive. '24. Group 1. Group 1. Group 1. Group 2. Group 2. Oops. Group 2. Let's see. Group 2 is in there. Uh-oh. No, yeah. Okay, group 2. Now you must have it. Oh, I forgot to mention, right? The lab 1 and lab 2 are due today, right? I forgot to mention at the beginning. Don't forget to upload your spreadsheet of lab 1 and 2. Okay. Don't forget to use the proper, the proper title. Okay, group 1. You gotta use this title here. P07 L01 G1. Please change the title. Okay. I need to have your information on the group number. Let's see, group 3 now. Let's go for group 3. Let's see. Blah, blah, blah. Lab 1. Well, I need lab 2 there. Group number 3. Did you put lab 2 there? Okay, we had our meeting for lab 2. Let's see here. L02. 02. Okay, looks good. Okay, now. Windows. Now I will open them again. Come up with the copies of those. Group number 9. Taking time to open. Here, good. Lab 3. Yeah, let's put here in my notes, right? Or which I didn't do it. Don't forget lab reports, spreadsheets for lab 1 and 2 are due today. Later on, I will brief you on the hard copy document for the reports. The reports are due today. And let's see here, lab. Huh. What's your notes? For my lab notes. Oh, here you go, lab notes. I don't have my lab notes here for some reason. Okay, so I gotta do that from scratch. Okay, so first, okay, I believe I mentioned that to you before, in case I didn't. Resistors. Resistor Wikipedia. Okay, Resistor, you know. Okay, that's how the resistors look like. Hey, there are a few other resistors that look a little bit different from that. Do you see the color code here in the resistor? Okay. Back in the times where multimeters were very expensive, people would know the resistance by reading the colors of the resistor here. And each color represents a number. I'm gonna copy that. Okay, each color represents a number. Each color represents a number. Okay, you're reading from the left to the right. You can find out what the resistance value. And here in Wikipedia, let's take a look here. We have, let's see, the code, the color code. Let's see, they don't have the color code here, unfortunately. It's not difficult to find this color code in the internet. Now, for some reason, they didn't put it here. Yeah, do you see the colors? The colors, yeah, that's power. That's not the resistance. But let's say as part marking code must be here. Nope, that's okay. We gotta go elsewhere. Resistor, color code. Okay. Right here. Each of those codes, either of those colors represents a number. Okay, okay. There are, I'm gonna write it down here. Finding the resistor, the resistance value by using the color code in the resistor. Okay? Most resistors have 4 color codes. Right? Most resistors. A few out there have 5 color bands. Let's put here colored bands. Let's put this way, colored bands. Colored bands. The color of each band represents a number. Okay? Let us concentrate on the resistor with 4 colored bands. Okay? With 4 colored bands. The first color from the left to the right represents the first significant digit of the resistor, of the resistance value. Okay. The second color code from the left to the right represents the second significant digit of the resistance value. The third color code from the left to the right, represent not the third significant digit, no, that's where things start to, represents the multiplicative power in the base of 10 of the resistance value. Okay, and the fourth color from the left to the right, okay, is starting from the left to the right. 1. The first color code represent the first significant digit of the resistance value. 2, the second color code represents the second significant digit of the resistance value. 3, the third color code represents the multiplicative power in the base of 10 of the resistance value. And for the fourth color code, what does it represent? Going back here, you're going to see it. The tolerance value, the tolerance value of the resistor. See that color? And each of those colors has a numeric significance. Okay, the fourth color code represents the tolerance of the resistor. What means the tolerance of the resistor? Tolerance of the resistor is a range of values for which the manufacturer guarantees the value of the resistor. Okay. So here you go. Example. Let's look at an example here. I'm going to get the example from Wikipedia. Okay. Here you go. Not this one. Let's get this one here. Yellow, violet. That's what? Orange, right? Yellow, violet, orange, and that's silver. Okay. Example. Yellow, violet, orange, and silver. What is the resistance value and its tolerance, right? Solution. Yellow. Let's take a look at the yellow. The numeric value of the yellow color. Here you go. Numeric value of the yellow color is 4. See that? That's the first band. Yellow. 4. Violet. Violet is 7. And the third one, orange, is the multiplier power. Orange is 3. Okay. It's 3. And then silver is the tolerance is given us in terms of percentage. Silver right in here, 10%, plus and minus 10%, plus and minus 10%. Okay. As a result, this resistor has the following value: 47 times 10 to the cube, and the manufacturer guarantees a tolerance of 10%. Okay, so this resistor there in Wikipedia has a value of 47,000 ohms. 47,000 ohms. Like that. And a tolerance value of, tolerance value of what? 10%, right? 47,000, don't forget, only 2 significant figures here, right? In this case, you have to write in terms of the scientific notation, plus and minus, 470. And don't forget, you have to write down that in terms of the significant figures. So you have to write in this way. Okay. So the manufacturers guarantee that the value of the resistance would be between 47,000 minus 470 and 47,000 plus 470. I mean, that's not second, not the third power. It's supposed to be the second power. Okay, that's what the thing here means. Okay, so when you go here to a spreadsheet, the color code is what we call the nominal value. Okay, and here you already have the values that they read from the color code. Okay, and then what you have to do, you have to display all those numbers in terms of the significant figure. Here is minus 10%, here's plus 10%. This one here is 15,000, right? 15,000 minus, this one here gonna be, yeah, that's minus 10% and plus 10% in my case, right? And here's the measurement of the DMM. In the case of significant figures of the DMM, you have to use that table, that table that I provided you to display the proper number of significant figures. Okay. So the first thing I want you to do the following. One, plot. Okay, plot nominal value versus DMM value of the first table. Plot nominal value along the y-axis, along the x-axis, and DMM value along the y-axis. Table 4-1. That's the first thing you gotta do. Then you go for the next. Repeat for the other two tables. Plot nominal value along the x-axis, DMM value along the x-axis for table 4-3. Table 4-3. Resistors in series. Okay. Plot nominal value, DMM value along the y-axis. Table 4-4. Yeah, 4-4. Okay. Notice that it's explicit here that R1 and R2 in series, R1 and R3 in series, and so on, right? Here is R1 and R2 in parallel, so on. Okay. Let's do that. So do the following. Plot the nominal value along the following tables. For the following tables. Table 4-1. Table 4-3. And table 4-4. 4-5 or 4-4. You can put 4-4. 4-4. Resistors in series. And resistor in parallel. Like that. Can you do that? So the first thing you gotta do that is this one. Okay, I'll give you some time there to do that. Okay. And here you go. Though what you're gonna get is that because those values are so close by each other. Why is that? Oh, I got the wrong one. This one here. Okay, now I got it. That's for my spreadsheet, right? You can see this nice straight line. Because those values are very close to each other. When I put the trend line with the regression equation, we are going to see that. Let's do that again. I'm gonna put here the trend line with the regression equation. We're gonna see that the slope of the trend line is very close to 1, right? Make sense? Okay. Then you do the same here for the resistors in series, right? Nominal value. How do I come up with the nominal value? I just sum up R1 with R2. Nominal values of R1 and R2, right? Nominal values of R1 and R3, R1 and R4, R1 and R5, R1 and R6. Insert like that. And then what do we get? Display, okay. Close to 1 as well. But what about this value here? Intercept value. Well, it's an error. It's an error, basically. Ideally, the slope should be 0. But it's not. Okay, and then you do the same here. 1 over Rj. And the DFM value. See, I put the inverse, right? Why I put the inverse? Because of the values of the equation, right? Like that. You go. Resistors in series are equivalent. R1 plus R2. R2, right? But resistors in parallel. 1 divided. It's like that. 1 divided. Like that. 1 divided. Like that. Okay. So what am I doing? I'm just plotting the inverse of the equivalent resistance for the table for resistors in parallel. Okay. 10:59. Any questions? So I'm gonna get here to my roster. P07. We are almost there at the plot graphs. I'll give a little bit of time. 10:56. I think we could have a break, right? Yeah, let's have our break. 10:56 right now. Break from 10. Unless you have a question, 10:57 to 11:12. Is that right? Yeah, that's right. AM. And until there, hopefully you already have your graphs, right? I see you in 15 minutes. I am back. Okay, so let's see how Jacqueline. Hi, Jacqueline. Did you manage to plot the graphs? 1, 2, 3 graphs that you should all plot. Let's see here. Okay, good. So once you plot the graphs, right? You go ahead and let's see, right? Oh yeah, you fill up this table, this part of the table, right? And also the other table here, you get the percentage difference, but just the slope, okay? Slope value units. Okay. Okay, so Jacqueline did that. Yorgo is not here today. Giselle, did you manage to plot all three graphs, Giselle? Let's see, Giselle is no longer here. Okay, I'll put, she left. I'll put a star here. Paul, did you manage to plot the graphs? Yes, okay, good. And the next thing that you have to do, right? Fill up tables. A table, let's see here. (4-5). I didn't put a number to this table. Let's see. (4-1) and (4-5). Fill up table 4-1. No, 4-2, right? And 4-5. Tables. Next one is Vanessa is not here. Vanessa Calera is not here. Norberto Lopez, are you there, Norberto?
Yeah,
Okay, did you plot all the three graphs?
yeah, I was able to.
Okay, good. Next is Vanessa Mena. Yes, okay, good. Sky, did you plot all three graphs?
Yes.
Okay, thank you. Ashley. Ashley Zumo. I can't hear from Ashley. Okay, let me put a star here. And about Corina, did you plot all the three graphs, Corina? Yes, okay, good. So let's go for table 4-2 and table 4-3, 4-5, right? Jacqueline, you fill them up? Let's start one table at a time, right? Otherwise, it's too much work. Table 4-2, let's see how I'm gonna do that. 4-2, table 4-2, table 4-5. Did you fill up the table 4-2, Jacqueline? Yes, okay, good. And what about table 4-5? You need that too? Yes, okay, good. So Yorgo is not here. Lizelle, do you manage to fill up tables 4-2 and 4-5, Lizelle? I don't see Lizelle. Yeah. Okay, I'm gonna put that O here because she disappeared, right? She was initially here, but then Zapata, did you fill up tables 4-2 and 4-5? Yeah. Vanessa is not here. Next is Norberto. Did you fill up tables 4-2 and 4-5?
Yeah, I was able to.
Okay, thank you. Vanessa Mena? Yes, okay. Sky?
Yes.
Yes, okay, no big deal, right? Easy, that's easy doing, right? Ashley? Are you there, Ashley? Ashley, so sorry. Okay, I've done them. Okay, what about the graphs? The graphs too, right? The graphs in the tables. Okay. Next is going to be Corina. Your turn, Corina. Yes. Okay. In 1120. So what's next? Table. Okay, fill up. Let's see here. Table 4-2. Table 4-5. Next in line is take that. Okay, 4-2, 4-5. Next, what I suggest you to do, fill up the units. And just recall, don't forget, here, units here, 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 and here, right? And then here, there are no units here, but there are units here. And let's not forget, there must be units here as well. Don't forget that I am calculating the inverse of the resistance, right? Here too is the inverse of the resistance. Here's a measurement. You have measurement in ohms, but here is the inverse of the resistance. So you gotta get the units right in here and then the units here as well. That's what I want you to do right now. Units. I'll give you a few minutes to work on that. 1120. Next is gonna be sig figs. And CL. Those are the other three that needs to be done. Sig figs, you have to use the table that I provided you. Okay, fill up the units. Display the proper number of sig figs using the document provided. And the document provided is let's see, where is the document? I gotta go there to Canvas. Course. There you go. Let's see. Lecture. Oh yeah, this one, this document here, right? What happened here is not displaying anything. Okay. Coming online. Gee, it's taking a long time. Let's see if I can find my hard drive. I'm not gonna wait that long. Sig figs. App slide, illustrations, and Red Lab report. Oh, here you go, this one here. Okay, so we're looking at this table right here on the resistance. Okay. Depending on the value of the resistance, you're going to have different values of significant figures, anywhere between 3 to 5, depending on the value, right? And as a reminder, don't forget to fill up your names here as well, right? And the dates. But only the names of those students who participated in the lab. Notice that the first graph has 1, 2, 3, 4, 5, 6 data points, but the second and third graph has only 5, okay? 1, 2, 3, 4, 5, right? So watch out for that. So when you're using n here, make sure you put the right number of data points in the graph. Here's the other graph. Insert. Okay, here you go. Straight line, add trend line, display R square. That's what we have here. You can see that this slope, this intercept ends up being very small. Whereas the other intercept is also very small compared to the values in question, right? We're talking about 50,000 here, 40,000 here, 30,000 here. So 152 is negligible compared to those values. And the same can be said about this one. The values are anywhere between 5,000. Let's see the actual value. It doesn't say, let's see. That's odd. Okay, anywhere between 5,000 and 30,000. So this value here is very small compared to them, to the values in question. And what about here? 10 to minus 5. 10 to minus 5 is not that small compared to those values, right? It's comparable. Maybe 10%. A little bit more than 10%. If here is, you know, 1 divided, yeah, a little bit more than 10%. So let's go to Jacqueline. Hi, Jacqueline. Did you manage to get the units? All the units? Yes? Okay. So Yorgo is not here. Gotta put the O for everything here. Let's see, Lizelle. Why do I have Lizelle? What happened? Lizelle is not here anymore? Okay. Yeah, Lizelle is not here. Okay, next in line is Paul Zapata. Did you manage to fill up all the units, Paul? Yes? What about the sig figs? Did you finish the sig figs as well? Significant figures as well? Also, oh my. Okay, what about the CL? What about the CL? Did you manage to do the CL as well? Or are you still working on it? No, okay, good, thank you. What about Norberto? Did you finish the units, Norberto? Hello, Norberto. Okay, I'm gonna put a star here, Norberto's name, and let's go to the next, Vanessa. Vanessa Mena, did you finish the units, Vanessa? Yes, okay. What about the sig figs? Did you finish the sig figs? Yes, okay. What about the CL? Working, okay, thank you. Sky, units, did you finish the units, Sky? Yes, well, oh, including CL? Okay, good. Okay, so work a little bit more on the graph, make sure everything is nice there in the graph, right? And let's see. Next in line here is Ashley. Hi, Ashley, did you finish the units? I'm working on CL, but the other ones too. Okay, that's good. I'll put W here for working. Corina, units, sig figs, and CL. Yes, including the CL. All of them. Okay, I'm gonna assume that yes. The first two, but the third one you're working on that. Okay, going back to Jacqueline. Hi, Jacqueline. Did you finish the sig figs? Yes, and what about the CL? Yes, too? Oh, okay, good. So make sure for those who finish everything, make sure your graph is also in good shape, right? If you like mine right now, it's not completely finished, right? Like I still have to optimize the graph, the axis, both along the x-axis and the y-axis. X-axis around 20,000, y-axis should be around 20,000 as well. Let's see, 20, 1, 2, 3. Yeah, okay. And those numbers, you know, they don't look good because the 3 is repeating 3, right? So you have to put another decimal places there, one decimal place there. Let's see if I can do that. Decimal place number, yeah, I'm gonna put just one decimal place here. Yeah, 2.5, 3.5. Now we have it. What about here? We have to do the same, right? Scientific, one more decimal place. And then you gotta do more. You have to both face it. It takes time to do that, right? But that's what you have to do in actual papers. You have to display it nicely so everybody can read it properly. And we have to add as well the chart design, add chart element, axis title, right? Primary. Okay, and so on, right? Let's see if I missed anybody else here. Norberto, are you there, Norberto? I don't see. 11:32. Norberto is not. I can hear from Norberto. And let's talk about the format of the hard copy, right? I have a sample here. Let's see, it must be this one. Oh yeah, here you go. Here's a sample. Okay. You don't have to do that for lab 1 and 2, but you have to do that for lab 3 on. So here you go. The explanations are there in the syllabus. So physics lab report, physics 7, lab 1, would have been electric field, but now this one that they're doing is lab 3, resistance measurements, right? And then you put first name, family name, and first name. family name, comma, first name, and so on, right? And group number and the date that we performed this activity, okay? Then in the next one, you copy and paste the tables that we have there in the spreadsheet, okay? Just copy and paste. And make sure you format it properly. Okay, format it properly. Don't break down the table in 2 pages. Let's see what happened here. Yeah, one must be close. Here you go. This one must be next to the other one. Okay. And this one here just in a single page, so it looks nice. Okay. And then you put the graphs as well. Copy and paste. That would be the graph for the quick potential. Insert, page break. But wait a minute, there is the electric field lines here, right? The electric field lines are missing in this one here. So I'm gonna look for that out, the graphs. There was only one graph. Well, 2 graphs if you count this one, right? One graph here, another graph here. And those graphs, they're not, they don't have the title axis, the axis title. They have too many zeros here. Make sure you don't have too many zeros. You know, put the least numbers of zeros that you can. If I were you here, I would stop at the second decimal place. And in this one, I wouldn't put any decimal places at all. Just put 1, 2, 3, 4, 5. Okay. That's how. So that's what the hard copy means. It's not much. It's very straightforward. The date that we did the activity. Okay. And the next lab report is going to be due. Let's go. Here you go. Display proper non-significant figures. What else? Fill up the units. And CL. Work on table is at 4-2. Yeah, that's 4-2. Finish table 4-2 for CL. Huh? Finish table 4-2 for CL. Okay. Next, this lab report, the report of this lab is due March the 20th, 24 next week. And let's see how we are doing with the next exam. Oh, next exam is still after. No, we have plenty of time for the next exam, right? It's gonna be after the spring break. So we have plenty of time to cover that. And okay, I think we covered everything. I wish I had the lecture for another half an hour. But next time I'm going to do that. I'm going to start lecture for 1.5 hours, right? And then use the remaining time for the lab. We can do those labs in a rather quick way. Any questions about that? Any questions about any of the material we covered today? Okay, so I'll let you go earlier today, and next time I'll plan better. And we'll meet again on Monday. Okay. So see you. Thank you, Paul. 6.